Hi guys, welcome to the OLED Waves paper reading channel. Today, we're trying to read the latest video generation paper by Meta. Its name is Movie Gen, a cast of media foundation models. The paper was just published this month, October 2024. I think in the beginning of the year, everybody was amazed by OpenAI's Sora, the video generation demo. And after that, people are trying to, especially the researchers, are trying to understand what technologies has been used in the Sora video generation. But after half a year, it's not until Meta published this paper, nobody has reviewed how the thing exactly works. Although I think there's some other papers published, they only talk about the general principle of the movie generation. But today, the Meta's work, which is a 90 pages of you can either call that technical report or paper. I personally think this is technical report because if you see the content of it, it's fairly detailed. Suppose you have a data, suppose you have a gigantic GPU cluster. I don't see why you cannot replicate Meta's work or build your own video generation service or model. Okay. But today, I just want to first see if I can finish the overview and the model architecture session, which includes why they're doing this, and the input and output, and roughly about what the training is about, and some details in the training. But I won't be able to cover the evaluation and the analysis part today. So I would call this part one, okay? Okay, let's start. I think that right now there are plenty of tutorials on what the movie gen is about. Our channel is more focusing on the papers or technical reports. Let's say we're in the end-to-end model era. Okay, so we're more interested in what the model architecture these people use and what's the implication of using this, and of course, more important thing, application studies. So let's take a look at the abstract because I think abstract is always the most important thing. First of all, they can generate HD videos, which is 1080p. And also they can generate video size of 16 seconds at 16 frames per second. I would say this is a little bit weaker than Sora because what I see from the Sora's demo, they can generate 1 minute, about 1 minute, which is 60 seconds of video in the high definition, right? And I think, like I said, it's more important for them to show the more technical innovations and simplification of the architectures, latent space, and training objective and the recipes, very important recipes. If you want to replicate them, even in a smaller scale, the Meta's revealing of the application studies are very important. And also, since OLED Wave is a data service and solutions company, we are very interested in the data curation. Okay. And also they talk about evaluation, how to parallelization, and how to optimize inference. So you can see it covers almost everything. And finally, yeah, like I said, or their true hope of this paper is it can help the research community to accelerate the progress and innovation in the media generation models, because I think you have to publish, keep the community alive. And there are videos, and I don't want to show them today, but you can definitely check it yourself. They are very amazing, I would say. The introduction, I think for those of you who are familiar with Sora, I think this is not that necessary. Yeah, I think they mentioned about important things in video generation, which is to predict realistic properties about motion, scene, physics, and geometry, audio, and etc. I personally think that the physics part is difficult to synthesize. And also it's hard to evaluate whether it's synthesized correctly or not. So I'm gonna skip the introduction part. Yeah, I think it's in the paper, so you cannot see the video part. But you can see that this is a general application of these type of movie generation models or video generation models. You can either go from text to video or text to image. And while you're synthesizing video or image, you can also do personalization and make sure the movie is consistent. And also you can have your own prompt. You can tell the synthesizer what type of movie you want to synthesize, especially in the video editing part. For example, moving one object in the movie or image to another part of the image or video. And also most of the video generation model just synthesize video nowadays, but sometimes you do want to come or add an audio track to the video, so it's AV. So you can see, I would say right now, if you look at, I'm a speech on audio person, but right now, if you see how the audio is being added into it, it's just, I think, to me, if you look at the spectrogram, it's a little bit abrupt, and because there definitely have some inconsistencies in the audio. But let's see what they do. Okay, the overview part. First of all, their model size is 30 billion parameters. So before today, nobody knows how big the movie generation model should be in order to generate those HD videos. But Meta gives us an answer. I think it's dozens of billion parameters should be okay. And also the model for generate the audio, I think it's less trivial to people, less important to people. But it says it's also 13 billion parameters. Many people say that, okay, this is not big compared to LLM. I think lots of LLM, there are thousands of billion parameters. But I want to mention that for LLM, the input token size, a lot of time, it's not that many compared to video or audio. So the computation cost of the video generation is really, really heavy, because they have to keep they have to have a very large what do you call that? Not only the computational cost is heavy for video generation, but also the memory cost for the video generation is very heavy, because right now in this paper they don't do they run a bidirection bidirectional attention, so they put everything into the video memory. So in order to synthesize long length audio, they do have to have a big memory of their GPU cards. All right. And I think this is interesting to me. What they observed is that it not only learn in the movie generation audio model, it learns not only the physical association, but also the psychological associations between the video and the audio world. I only finished the model architecture part by far, but I really interested in how do they demonstrate it has the psychological association in a engineering paper like this. Personalization. Yeah, they're talking about the definition of the personalization, and they're talking about the definition of what is precise editing. Okay. They're talking about joint image and the video generation. So they show their training recipe in figure 2. So you can see I skipped lots of the references. For instance, this is very important. I don't have time to read it today. I might have a paper talking about this. It's called flow matching. It's a very fundamental model for people to use in the video generation. The concept originated from physics. It's about how to model the mechanisms in the flow. But computer science people borrow that from physics. And it works surprisingly well for training a VAE-like encoder and decoder, so they can synthesize a video from a Gaussian-like noise. All right. Okay, this is the general architecture of their model. And this is for general public. It just allow you to see how the data flows, but they do have another figure telling you about model architecture. We'll cover that. But for this one, all you have to remember is this is the input. And they forgot to draw this. This is the video, okay, or image. This is their output. Okay. During the input, they put it through an encoder and then patchify to turn the matrix into a string of features, and then they send it to transformer blocks. So after encoder, they send it to the transformer blocks, which is, you can regard it as a it's actually a transformer decoders, right? And then you also have the cross attention. Why this cross attention? Because this is not self attention. So over here you have video and images, right? And over here the input are text. The text are sending through 3 encoders, and the 3 encoders output are then being added or concatenated. I think it's added. And then because this is from text, they use this cross attention to hook up this with the video generation networks. And in the end, you can see it has a symmetric or TAE decoder. TAE means temporal autoencoder model, because they have extended the image generation to video generation, which in video generation they have the time, okay, which is temporal. Okay, and also because this is generation, they have this Gaussian noise here. You might ask, why do they need a Gaussian noise and the image as 2 inputs to the transformer block? Because they're using the features come out from the TAE encoder as the condition for the Gaussian noise video generation. Okay. these are the condition, and they're still using the Gaussian noise as the starting point for the video generation. Okay. I don't think I have lots of time to cover the details, but regarding the temporal audio encoder, I would just say that this is a frame interpolation models. The point of this, of course, first they have to encode the video or image. The second purpose of doing this is to do some sort of a compression, because although I think Meta has a lot of GPUs, they still wanted to reduce computational costs during the training. So basically, they compressing input by 8 times across each of the spatial temporal dimension. So this is time, channel, height, and width. So this is divided by 8, this is divided by 8, this is divided by 8. So I think they're reduced the computation cost by almost 512 times, right? This is huge. And I think they may not be able to do the ablation study because running the full size video training is very expensive. I understand that. And also learn some new things. I'm not a computer vision people. You can search what is symmetric or replicate padding. Since you're here, I just give you a quick overview. Suppose you have an image of like this, 3 by 3, 7, 8, 9. But if you do symmetric padding, suppose you just want to pad it an extra 1 pixel along each axis, then you just copy the 456 here and the 456 here, and you put 285. So this is, like you see, this is symmetric along the edge, along the edge, and this is just copy the digits here. And what is this? Yes, this is 5, right? 5. Okay. I think according to what I see, I can roughly get the mass from here. They're saying this is to reduce the abrupt result when the convolutional filter moves to the edge of the image. That makes sense to me. Yeah, they're saying this. This is why they're doing this. Yeah, so this is why this is what I have for the people who just started video generation research. This paper is also a very good source of literature review. Suppose you want to work in this domain, I guess you have to read the papers mentioned in this paper, referenced in this paper. And also, this paper is a very good source for the engineering people. So say you don't have a lot of GPU to tune your parameters, like they said, you can see they told you what's the parameter they use. For example, the channel numbers, and also the ratio of mixing image and the video, which is image is just a 1 and the video is 3 batches. This is a image 1, video 3. I don't know why they come up with this ratio. They may have do some experiments on their side, but they didn't tell us why. But I mean, if you want to do something like this, you want to start off with this ratio, right? Here is the TAE architecture. So you can see, of course, they reduce the what do they say that? Reduced the size of the input tensor by down 8 times along the horizontal along the height, width, and the channel, right? Not channel, sorry, the time. And later on they would have their decoder to upsample everything. But you can see every training or the subsequent training is conducted on these latent frames. You see, these have way less frames than the original latent frames extracted from the original video. So the cost is saved here. Why they're discarding this? According to what they're saying, they're discarding like mentioned here, spurious frames is gonna be removed. So I'm not a computer vision guy, so I really don't know what's the details of removing these frames, because do they remove the thing from the end, or they pick up some frames in the middle? If you know the answer to this, feel free to comment at the comment section of the video, but I think it's a trivial. But this is really detailed paper. I mentioned this for you to see. This is a very detailed paper. This is improvement to the training objective. Yeah, so you can see in the figure 5, this is what the abnormalities they observed, okay? And they zoomed in, you can have this, and they spotted artifacts, and they checked the latent space, and they found, okay, I found this. So in order to suppress those artifacts, they did. I personally think this is a very ad hoc thing. So this equation as a regularization term, the purpose is to prevent the latent variables values from deviating too much from the mean value. So you can see this. They set r equal to 3, and let me draw this. Suppose x is a normal distribution. So you can see this is the mean, and this is the mean plus theta plus 2 theta and plus 3 theta, right? Sigma, sorry. So all they have to do is, if anything falls into this region, okay, I would just clip, set a seeding value of this. No value should be above this one. Okay, very ad hoc. So and this is tau inference through the TAE, because in the end, suppose they want to have a very long video, or they have a very long input video. So say this is longer than 16 seconds. Let's say this is 60 seconds. All they have to do is they have to extract the tiles from the entire video. So this is 16 seconds, this is 60 seconds, but they have some overlap or on the video. So later on, so the latent can be, they use the word blended. I think the latent, to speech people, they're overlapped latent. Okay, well, that makes sense to me. So that I think from the philosophy point of view, this could remove the inconsistencies if you just have unoverlapped or non-overlapped tiles. Okay, that makes sense. The training objectives, I think that makes sense to me. Signal to noise ratio. They want to mention that it's important to use pure Gaussian noise samples. Yeah. I think they also mentioned that in other papers, other papers, of diffusion formulation, it's important to choose the right diffusion noise schedules with a 0 terminal signal noise ratio. Is particularly important. So this meta paper gives us important experience in doing this. So for those of you who are interested in why they need a 0 terminal SNR ratio, you can definitely check those papers. Joint image and video generation backbone architecture. Okay, this is I think most of the people are interested, but surprisingly, the architecture is fairly vanilla, I would say. Okay. How do I? Where do I start? I think I would start. Still start from here. Here is input. Okay. Input. You can see how did they come up with this 73K parameter. I will tell you where is it in the paper. I found it. It's on page 10. I didn't mean to complain, but this paper hasn't been peer reviewed. So the writing of the paper took me some time to get the information I need, because I can see that they're keeping repeating something but not fully explaining everything in one spot. But I have to look at multiple locations to gather my information. I think you may have the same impression as me. So the 73K tokens are coming from here. It's 763 by 763 pixel video with 256 frames compressed by this through the TAE encoder. And this is a patchification. Then you have this, okay? And after this, they have this type of shift and norm. I think they talk about the scale norm, right? I think. And so shift norm, regarding shift norm, I think they mentioned that they use a layer norm. Of course, embedding is important. If you're familiar with transformer use positional embeddings. But my question is, speech people use relative position embedding. Does it make sense to have a relative position embedding here? These are all the same thing as transformer, okay? And then here, you might say, okay, this is something we are familiar to, right? This is called cross attention. The contexts are coming from where? Coming from the text encoder, right? This is why they're showing this here. There are 3 context encoder. I think that UL2, long prompt, metaclip, and byte T5. And everything you can see that although they have a different input size, but in the end, they end up with the embedding of the same size, right? Okay. Then it's going to be capable of integrating the context embedding into the backbone. So the cross attention can be used to get the information from the text. And you can see every, I think from now on, from here, the embedding size is 6144. And the output is still size of the same size, right? It's still 73K. Okay, that makes sense, right? So I think lots of people may get disappointed here. They have a fairly straightforward or simple model architecture, and they can get such good result. I think this is agreed by lots of the researchers right now. In the area of deep learning, especially in 2024, it's more important to get your data right other than to develop fancy model architectures. People just, you can see the backbone is based on transformer decoder or encoder, and they just use the vanilla cross attention. They do use some their own developed models. For example, they do use some type of their SWE GLU as their activation function, and they do use some RMS normalization, which might be a little bit unfamiliar with you, but most of the things are very generic or widely used. Like I said, I mentioned that the text embedding, remember the cross attention, you go from the prompt. For example, you want to say, I want to have a penguin holding a sign, right? This is the text. And the text is supposed to be sending to 3 text encoders. The first is the UL2 is trained by massive text only data. So they're saying that it potentially provide strong text reasoning abilities. And also the meta clip, it's a clip model. They're just trained by Meta, so they name it as meta clip. This provides information of the alignments from text to visual representations. And they're saying this is good for cross-model generation. Okay. And the third model text encoder is called a BY5, a BYT5. It's just to encode the visual text. For example, like I said, it's a penguin or the bird, emu. So the emu, you can see the sign. It's just for synthesizing the text in the sign. Okay, so you can see the input. So for the input of the UL2 and the meta clip, they use everything, I think. But by T5, I think they're just using these or focus on the no movie gen is the best text. Okay, makes sense. I finished the text encoder. The backbone, also I mentioned that. FPS, I think 60 FPS is low. What do you think? But they can increase FPS to 24 in the end later on. And they also mentioned the interesting thing. I think it seems to me that the spatial sampling mentioned here is a little bit new compared to other parts of the paper. The reason behind this is because they still want to reduce the training cost during the training. And what they do is, so I think the writing took me some time. Maybe I'm a non-computer vision people. So this whole thing is spatial upsampler, not this part, not this part, not that part. The whole thing is spatial sampler, upsampler. First of all, they are just having a it's maybe a bilinear operation. Okay, to first sample the low resolution video to the upsample videos. But I guess the quality of video is still not very good in this bilinear upsample video. So then they apply a image autoencoder to get encoded features. Then they use the encoded feature as a condition for the latent noise to generate high definition videos through a image autoencoder's decoding process. That makes sense? So the key thing is that they put encoder feature as a condition to the latent noise, and you can this part and this part are VAE encoder and decoder. Okay. Implementation details. This is a very large data set, I would say. 400K HD videos. So I'm more like an engineering guy, so I'm very sensitive to these numbers. Very amazing amount of numbers. This is just for, I think it's just for showing off. People just say, okay, we have this amount of GPUs and we have our GPU memory is this big, and we have this type of RDM NICs. Just come here and work for us. Okay, I'm almost there. Regarding the pre-training, I may have a separate session of the data, but I just quickly go over the pre-training section. Okay. So they may have a lot of raw videos, and then they apply a series or consequently processed the videos with low visual qualities. Okay, and as shown in the figure below. I think this is the most sophisticated one because you can see so many rules are mentioned here. I think motion filter is relatively straightforward, and content filtering. What does that mean? They remove the perceptually duplicated clips. Captioning. Interesting thing is they do not use human being or human tag, because you can definitely, if you go onto the Flickr like a website, you can have find many human captions. But here, every caption was generated by their Llama 3 video model. Okay. And this one is called multi-stage data curation. I think this part is a little bit not so clear to me. First, they mentioned that they curated 3 subsets of pre-training data with progressively stricter visual motion and the context threshold. It means it's related to this one, right? These 3. And then they're talking about the procedure of doing this. So my understanding is that they use this first, next, and finally for each subset of these to get each subset of pre-training data. Okay, I think this might be a typo, because first they come up with a low resolution training and they have a minimum here. I think it should be maximum. Might be a typo here. And then they figure out the minimum width and height for high resolution training. Finally, they curate a new video augmenting their high resolution set. But I think this doesn't have anything to do with the visual motion and content, right? So does that mean that after they get each 3 subset, and then they apply these first, next, and final steps? Yeah, I think to get the more details, you might have to read the appendix B.1. The other thing is the bucketization variable duration and size. And this is the progressive training recipe. This is what they first start off with. And then the next step is they train with this image and video clips. And in the next step, the third step, they train with higher movies or videos with higher resolutions, right? You can see this. And then this is second step. This is the first step. This is the second step. This is the third step. From first to second step, the videos are added. But in the third step, the high resolution video are added. Okay, this is what they talk about in the training stage. Fine tuning. Well, the fine tuning are, I think, they might want to write in more details, because I think this is probably the key or the holy grail of why the thing works. First, there are 4 stages are running in sequence for their fine tuning. First, establish a set of candidate videos. And they mentioned that they used some type of automated filter that set a strict threshold on aesthetic, motion, and scene change. So here's my question to these researchers. How do you make sure that your automated filter are doing the right thing? So this stage, they result a few millions videos. So this is way less than the raw videos. I think this is just filtering first. Then they balance the concepts in the videos. That they use some sort of KNN method to cluster those concepts, right? Yeah, and the features are based on the taxonomy of human verbs and expressions. Well, that makes sense to me. Well, the third and fourth stage might not be easily done, because this, you can see, it all has the word manually. That means human beings are involved here. Identifying the cinematic videos. Okay. And then also the caption the videos. Right now you can see that at this stage, they do caption the videos. I think in the previous stage, I remember I mentioned, had the doubt, the caption part, the caption of the everything was generated, right? Yes, the captioning, right? In this pre-training stage, the captions are prepared by a Llama 3 video model automatically, but in the fine-tuning stage, they do have human beings to manually annotate the videos, and aka captioning the videos. The recipe, they use less amount of GPUs. Inference. I think inference is pretty much engineering. I will skip there. So, okay, Let's say today we finished up to 3.4 before the evaluation. I will stop here. In case you have any questions, feel free to comment in the comment sections. Let's discuss. And this is OLED Wave paper reading channel. We're sponsored by OLED Wave, a data service company. We provide pre-labeled training sets, data sets for training your GPT-4o-like models. And we also provide data service. Thank you for being with us. Please don't forget to hit the subscribe channel. And let's meet next time. I will read the evaluation part and more parts of the video generation paper. Bye.